Hi, my name is Harsha Patil, and this is Lab 4 for Physics 2212. Some of the fundamental principles that you need to know for this lab include circuit rules, loop and node rules, Ohm's law, energy conservation, charge conservation, resistors, batteries, ammeters, voltmeters, capacitors, parallel series circuits, resistor capacitor circuits, or RC circuits, and understand time dependence. Linearization is also a key component, as we'll apply this to our calculations later, and it is also important to understand quasi-steady state. Here are some important formulas used for the following experiment. One important key formula that I will draw attention to is the very last formula, which is used to calculate RC. So I found that value to be 6, and this was consistent across experimental and modeled results. This is a circuit with 2 ammeters, 2 resistors, and 2 batteries. The current I found was 0.02 amperes, which was the same as if the ammeter was connected backwards, so the value remained positive. So the currents in both the wires were this value. When I replaced the ammeter with a voltmeter, the current was equal to 0.02 amperes again, and the potential difference was 3 volts. When the circuit was closed, the potential difference for the battery was 3 volts. For a resistor, it's 47 ohms was negative 0.959, and the potential difference for the resistor with 100 ohms was negative 2.041 volts. So the total potential difference resulted at 0. As you can see, this is a graph depicting the potential across different points of the circuit. The battery raises the potential. The resistors lower the potential, as you can see in this downward trend, and our calculations before indicated that the potential value was negative with the resistors, and the ammeter has little to no effect on the potential difference, as its resistance is about 0. When you attach the voltmeter, you alter the circuit. Why doesn't the ammeter reading change? Well, the voltmeter has a high resistance, which means little flow of current, so the ammeter reading doesn't change that much. Now, what happens if the ammeter connects in parallel to the 100 ohms resistor? Well, both ammeters would be at 0.06 amperes. Below, I've calculated the resistance for each of the following circuit elements. So resistance equals delta V divided by I, or potential difference divided by current, and you can see those calculations below. What happens to a bulb when the battery is connected in a series RC circuit? Well, these are some more questions about part B. So the bulb brightens and then dims slowly until it goes out. What happens to the bulb connected in a series to the charge capacitor? The bulb brightens and dims till it turns off, much like the previous scenario. And then what happens to the current in both scenarios? Well, the current is very large and decreases to 0 over time. So the time taken for the capacitor to charge or discharge the following bulbs is as indicated, 9.4 seconds for the bulb with 10 ohms of resistance and 18.1 seconds for the bulb with 20 ohms. This is an image of the setup of my experiment where I discharged the capacitor over an amount of time and recorded my experimental values. So here's the experimental data for this experiment. As you can see, we simplified the first expression, Q over C minus IR equals 0, and then finally ended up with the natural log of the potential difference over the original potential difference equals negative T over RC. So this linearization of the data allowed us to plot the data points in this linear fashion on the graph, and the slope of this graph is negative 0.1701. Here are my calculations, and I found the RC to be 6, as we did 30 ohms times 0.2, and our percent error was 2% error. To answer a few what-ifs, if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter, what would be different about the real ammeter and how would it affect the circuits? Well, the real ammeters have very little resistance, so the current would drop overall because it is inversely proportional to resistance, and if there is some resistance in real life, then the current would actually drop. Now, the second what if you're doing this lab in real life and used a real battery and capacitor with no resistor in the circuit, if the only components are battery and capacitor, it would charge instantly almost instantly because the only voltage drop would be from the capacitor, and the resistance from the battery is minimal, and there is no major resistance from the circuit. So yeah,